Resistors in a circuit can be placed in various configurations. The two basic types are going to be series and parallel. In the series configuration, some of the important things are that the current remains the same, but the voltage depends on the resistor. Now, to find what we call an equivalent resistance, we would add up all of the resistors, and that would give us the equivalent resistance. For parallel, on the other hand, we do have the same voltage. They have the same voltage, however the current is different. So notice that these two end up being switched as far as series and parallel are concerned. We'll show you what these look like, of course, in real actuality. In order to find the equivalent resistance for parallel, however, this gets a bit trickier. So this is going to be the sum of all of the reciprocals.
Awesome!
Everything is awesome.
Could you say that again, please?
Awesome!
Everything is awesome.
So what we do is we add up all the reciprocals, get an answer, and then we reciprocate that answer. We will show you what that means in a bit. Let's show you what a series looks like. So we're going to go ahead and draw a circuit. It'll have a voltage. So here we're going to draw a series configuration of 3 resistors. Here's our battery. Here's our wires. There are multiple ways to draw this, but I'm going to draw in the most simplest way I can think of. Here are 3 resistors, our 12-volt battery, our 2 ohm resistor right here, 4 ohm, 10 ohm. You'll notice that as the current leaves a positive terminal, it's going to go over this resistor and then this resistor and then this resistor. Each resistor in turn will give us a voltage drop. But the current doesn't have to find the path of least resistance because there aren't any options. It'll go ahead and go through the series of resistors. To calculate the equivalent resistance, recall that for series, in order to find the equivalent resistance, we're going to go ahead and add these 3. Now, equivalent resistance simply means that if we were to take all of these resistors and do the appropriate combinations, we're going to get a super resistor, if you will. Okay, so instead of having all 3 of these, I could express these as one resistor, and this equivalent resistance would be, in this case, 16 ohms. So what I'm proposing to you is that we could essentially redraw this, but all 3 of these resistors cannot be drawn as just one resistor. So that's what equivalent resistance means. I took the 2, the 4, and the 10, and now I made it into a 16. Okay. Now to find this current, we would of course use Ohm's law. When you do problems of this nature, please do your best not to run until the end. It is very important that you don't do that. Here we have a parallel configuration. Notice that as the current leaves this battery, we come to a junction, right? And the current has to make a decision. So if you find yourself looking at a circuit and you're following along on the wire, and you get to a point where you have to make a decision which way to go, that means you have a parallel configuration. Okay. So in this case, you can either go this way with a 2 ohm resistor, or could continue down this wire where it's going to experience a 6 ohm resistance. Okay. Now, when it comes to parallel, we know the voltage remains the same. So the 10 volts that are being applied from the battery are applied to not only the 2 ohm resistor, but also to the 6 ohm resistor. So because it's parallel, the voltage stays the same, and the answer to A is simply 10 volts. And that's because it's parallel. However, in a parallel configuration, the current does not stay the same. The current depends on the resistor itself. And so what we do here is, knowing that the 2 ohm resistor has a 10 volts applied over it, we can calculate the current as V over R. And we get 5 amps going down this branch. Just to do a conceptual thought experiment, knowing that this resistor has a lower value means it's going to express less resistance. And if there's less resistance, that means more current is allowed to flow. If you look at the other branch, we have a higher resistance. So you would expect there to be less current going through this branch of the circuit because it has more resistance. Essentially, the dam is stronger and that part of the river, right? And so less water is going to flow through. I'll leave it to you as an exercise if you're interested. However, the current going in this direction is going to be about 1.7 amps after you round up. Okay, that confirms our suspicions. Summary: what are the differences between resistors in series and resistors in parallel? Resistors in series. Good golly. Problem 3, we're starting to look at more believable problems in real life. So here we have a mess going on, right? If we were to go ahead and follow the current out of this battery, we're not having to find an option here if we're going to cross the 2 ohm resistor or not. So that's not the issue here. The issue is when I get to this point, I have a choice to make. I either go down or I go right. And then if I do go right, I hit another junction and I either go left or I go right. I mean down or right. Now, interestingly enough, folks, the current is conserved at the end, and so is the charge, because what happens is whatever current I have going this way goes over the resistor, comes back, and it joins with this current going down here. And then this combined current goes through into the final junction, meets up with this current from this branch, and then we have the full current again going into the EMF device and being pumped out. It's very fascinating. Very interesting. We're going to find the equivalent resistance. We're going to first begin with this parallel configuration. So all 3 of these right now are in parallel configuration. If I do parallel, remember, this is the tricky one with the equivalent resistance being the reciprocal. So I'm going to do 1 over 4, 1 over 6, and 1 over 10. I am not doing this 2 ohm resistor up here because that is not in parallel. We didn't have to make a decision about that resistor. That's actually, this 2 ohm resistor is in series with his entire blue setup. Okay, so we're first going to take care of these 3 resistors that are in parallel. Now, if I go ahead and do this, this is going to hurt some of you a bit. It is wise to do this by hand if possible. Okay, otherwise use your calculator carefully. But if we go ahead and we're to find common denominators for all these, and if you're wondering how did that happen, I need a common denominator for 4, 6, and 10. It ends up being 60. And then we go ahead and whatever you do to the bottom, you do to the top. Okay, I'll leave that to you as an exercise. However, please note that this is 1 over the equivalent resistance. This is not like series where we were able to just add them up and we're done. Here, what we're proposing to you is that the reciprocal of the equivalent resistance is 31 over 60 ohms. So I have to flip this upside down to get the equivalent resistance. So that, folks, is my equivalent resistance for this blue area right here.
I just cannot believe this.
For those of you wanting to do this in your calculator directly, I propose the following. So you're going to go ahead and add up all the reciprocals and then raise it to the -1 power. Raising it to the -1 power is going to reciprocate your answer. That essentially this whole blue region right here, these 3 in parallel, they can be redrawn as just 1 resistor with a resistance of 60 over 31 ohms. 2 resistors in series. Okay, you notice that as the current leaves here, I'm not having to make a decision where the current is going. It has only 1 loop to go through. So this is now a series configuration, and I can find the final equivalent resistance. So series, we just add them up. And for those of you that want an exact answer, it'll be 122 over 31 ohms. If we were to get a decimal value for this, it's looking like maybe 3.94 ohms. Having done that, we found a total equivalent resistance for the entire circuit. Now we're going to find the current leaving the battery. That's going to be the 12 volts over the 122 over 31 ohms. Putting that in your calculator, and again, I leave it to the listener to go ahead and confirm that with your calculator. I'm going to round to the nearest hundredth, and I'm going to get 3.05 amps leaving the battery. So for this exercise, we're going to give you three different resistors, RA, RB, or R1, R2, and R3. Okay, they have different values. They're unique. So if you want to make them 1, 2, and 3, perfectly fine. I want to show you a few configurations and have you finish the rest. So for example, if I had this setup, I could have the following, right? Or this. Or this. And that's because all three of them have different values. I could also have this configuration where they're in parallel and then series. Along with this setup. And this setup. And again, I'm allowed to do this because they all have unique different values. So we have shown you 6 unique drawings. There are 2 more that you should be able to come up with. And go easy on yourself. They're simple. In summary, what does equivalent resistance mean?